Sorry. No, I'm always erasing. I feel bad sometimes. What? Like whenever I'm erasing. No, it's like everybody can hear this. Yeah, I can. Okay, I feel like
Yeah.
Yeah.
Look like one sound, right? How much once? It's a long game. Where it's like, it's fine. Yeah, so it's much scary.
I think you do.
invited from both sides of the thing. That's what we did, but I still about why.
No, I just think so.
Well, cause.
First one, I was like, I got the can, like you got one half, right?
Yeah.
So I was like.
Something rough, bro. Second back. Because they were
The second one?
Yeah.
Because when we had.
Sailor. So you guys. You might get a role.
Because I thought it couldn't be higher than an honor special grade how much you use. I could only be close. Yeah, that's why you put it to the floor.
I didn't like.
Oh, no, you separated.
You didn't get one.
Oh, you
This is the last one.
used the way you showed us, like the. You want on this
This is
side and
oh, for next.
the X on the other.
Yeah, so I tried to do that, we have the y x squared, we got me sort of divided it. When I simplified it, I still got it. To the further.
You got it right? And then I wrote it out like that.
So you'll do one for me, like what's like this on the other side.
Oh, you can divide it.
Yeah,
That's
why?
what I did.
And then you simplify. You know,
So you
simplify the
got-
y.
I see.
You kept, I kept it there. So now it's.
And now, okay, so
Now
now
it's-
it's here.
Yeah, and then you move it,
It's starting close.
and then you move the, yeah, that's over here. dy, then dx. It's probably because like he tells us to write dy here for this, because it's easier to simplify that. Probably that's what, that's what,
But then the y doesn't hurt.
Oh, it's not bad, it's had CS, but it's, you know, so it's like.
Yeah, that's her on like, I don't know why it says.
No, I'm just.
Check. Check. That's all I can do is to jump.
problems are like electrical, like.
Did you divide into the students?
It was the first time you saw it.
It might be mixed.
Like, you know, that.
No.
Maybe that'll help me.
Was it? Yeah. Yeah.
I think you're just getting confused once you think the why thing.
Yeah. Oh, yeah, so all I had to do was do you want to go with my.
Yeah. And it's just like one,
Oh.
one over y. Yeah, it's like that. Okay, yeah, I think that's what you're going to go by.
Cause I don't know, my used to see that.
Why?
Yeah, cause so, my brother's like when people learn that stuff is more than you can do this, if it's more than you can library.
Yeah.
So then it's like,
Yeah, like he gave me
Yeah.
one of
That's pretty much fine.
or like for your reading.
Yeah. I don't remember those debate. How to solve it. For me.
Yeah.
Yeah. Staying matters. As long as you try.
No, for something. He does like to say they.
This one.
Yeah, this one, I think I finished. Yeah, like the name of it. I have all of the two. What I did, that I made an album. That's fine with me. Yeah, they get really tough. I made an album and then I just, I fit those pictures and I just made those black. I'll get some of the longer problems. Even the Jordans that you gotta. Yeah, that's pretty good. That's it. I think it was very social. No, because like also.
Yeah, but I think that.
It's weird, right? And he added, you can't really hide it.
Cause cause like everything else. Look at you, and it's with my.
The first one.
So I like, I would go back to these labs and learn for it and what I did.
All of their energy is what I got. Also, just this answer.
Kind of good.
All the other ones I got.
Yeah, I just know there's,
I tried.
like everybody. Like they'll, like they will get Walmart, they won't get.
And it's spoke out. I get it.
I think that's.
It's the same thing as.
There was some. I didn't read those, so.
Yeah.
Yeah, it's like. Oh, yeah. New driver's license or. Sure, or no, go to your phone.
Yeah. Okay. I want to say, picture of the sign, because I have rather than forget.
It's on your phone.
With your.
Yeah.
No,
Get it right.
last time. People after. Yeah.
Do you have one?
Maybe in the same.
Oh.
No, I just happy that happened.
Yeah. It's like, yeah. Someone back. I don't remember the one. I never remember.
He's. Yeah. We probably know about the file. I want to know where you were. Yeah, yeah, it's from school. How's that? Absolutely. How do we? Yeah.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good. Doing good, good. Has it set in yet that spring semester has started? Yeah. I know, right? I still feel, I don't know, it takes me a while to get into the spring semester. Okay, so today, we're just continuing where we left off, so more ordinary differential equations for everybody. So some announcements before we begin. Homework 1 is due this Thursday at 11:59. It's due on Canvas. So usually, you can scan people usually scan the homework, turn to a PDF and then upload it there. But of course, if you finish it early, you can turn it into lectures as well. Most of the time you'll see the homeworks due on Thursday, not every Thursday. That's crazy. I don't have the capacity to grade. But most of the time you'll have homeworks due on Thursday. That's mostly just so that, if you have final questions, you can make use of all the office hours in the week. You can ask me questions in the lecture, just to give you guys a little extra time. Okay. A little bit of information about how I grade the homeworks. So I grade the homeworks partially on completion and partially on correctness. So for this homework, for each problem on the homework, basically there are 10 points. Well, I should say this. So I only grade one of the homeworks. I only grade one of the problems on the homework for correctness. So out of the 4 problems, and I'll tell you right now, I usually don't grade the problem 1 for correctness. So it's going to be one of the problem solving questions. That problem is going to be worth 50% of the total points. The other 50% of the points is just, I'm going to go through your homework to make sure that, you did everything. It's on completeness. I see that, you did more than just write the problem down. Usually people in the past, they just kind of write the problem down. They expect to get completeness points for that. So you have to actually try to do the problem. So as long as you do everything, that's worth 50% of the points. And then whatever problem I grade, that's going to be the other worth the other 50% of the points. Okay. And then, and what I usually do is that on Canvas, I leave you a comment based on kind of how your score is broken down. So I'll give you a score for completeness. I'll give you a score for correctness. Okay. All right. So I think that's it. Any questions I can answer before we get started for today? By the way, I heard some people talking before class. So I write the problem every year from scratch. So I do make mistakes in my work, and so if you're getting a different answer than what I have listed on the homework assignment, just let me know. Oftentimes I'll be making a mistake in my homework solutions, and that's reflected there. So if you're trying a problem, you've done it 5 times and it's driving you crazy, you can't get to what I got. Likely I might have made a mistake. So just let me know and I'll go through my work again. And then I'll correct it. Okay. Okay. So where we left off last time was we were talking about first order ODEs. Okay. Okay. So there are 2 main ways to solve first order ordinary differential equations. So we finished talking about the first one last time, which was separation of variables. Okay. Basically, the idea with separation of variables is to manipulate the differential equation algebraically until it's in a state where you have everything that has all the y terms on one side of the equation and all of the x terms on the other side of the equation. Okay. The other method that we're going to finish up talking about today is integrating factor. Okay. So we started it last time. We basically just about got done with the derivation, but so we'll finish up that derivation today, and then we'll do a couple of examples to show you how it works. Okay. A question I get all the time in this section is, how do you know, which method to use? Okay. Because they're quite different in terms of how you solve the problems. Right. Generally, what I tell people is that if you can use integrating factor, that's the preferred method. And you can only use integrating factor if the equation is linear. or I guess I should be more specific. If the dependent variable is linear, which, most of our case is going to be y. Okay. It is possible to solve some linear equations with separation of variables. But it usually doesn't go the other way around. If the equation is non-linear, then there's usually no way to use integrating. Okay. And what does linear mean? Linear means that the dependent variable y only shows up in the first power. Okay. And technically that goes for the derivative terms too. So dy dx there and eventually d squared y dx squared. So the second order derivative, all of those have to have exponent 1. But even in this class, we don't deal with cases where the derivatives are non-linear. So what you're really looking for is you're looking for all the y terms. If their exponent is 1, then you use integrating factor. If you have terms where the y term is raised to a second power, third power, fourth power, that's usually a good indication to you that you should use separation of variables. Okay. So I think 2b on the homework is a good example of this. So 2b has a y to the fourth power. That's a case where you have to use separation of variables. So that's kind of like that's kind of a dead giveaway that there's only one way to solve this is with separation of variables. Okay. Okay. So with that said, let's finish up our derivation for integrating factors. Okay. So the way to solve a differential equation with integrating factors is we're going to take our differential equation and multiply it by another by a factor, which is called the integrating factor. Okay, and this function we usually give it the symbol mu of x. Okay, and that mu of x is our integrating factor. Okay. I don't know what it is. This class, there's a lot of weird noises happening next door. Hopefully, I guess it's going to be like that the whole semester. And so the idea with this integrating factor is that we want to turn the left-hand side of the equation into something that we can integrate straight. Okay. All right. So I'm not going to do the whole derivation again. I'm just going to kind of show you the main points. Okay. Okay, so here's our first order ordinary differential equation. It is linear because you can see that y only appears once here and y has an order of 1. Okay. And so the idea is that we're going to take this entire equation, multiply by mu of x. Okay. And so what that's going to do is that once and if we choose a very particular form for mu of x, which is kind of what we ended with last time, what that does is that it takes this entire left-hand side and transforms it into the following. So we have d dx of y of x multiplied by mu of x is equal to R of X times mu of X. Okay. So that transformation there, so going from that, you know, the left-hand side down there, that was kind of the derivation from last time. So, you know, right, if you look at it just like this, it looks like magic, but it's not magic, it's just math. So just, you know, I would say just look at the notes from last time. Okay. And this only works if mu of X, our integrating factor, has the following form. So it has the form e to the integral p of x dx. Okay. Where the p of x in the exponent there is the exact same p of x that was in front of the y in our original equation. Right. And then once we're in this form, we are good to go, because to solve for y of x, all we have to do is just integrate both sides with respect to x. WRT there stands for with respect to. So let me go ahead and do that. So if we integrate both sides with respect to x, so we integral here, integral this side. Okay. Oh, is my mic off? Oh, sorry. P of x includes the sign. Yes, yes, P of x includes the sign. Okay, and so we integrate both sides. On the left-hand side, the integral is going to cancel out with the derivative. And so all we're left with is y of x, mu of x. Right-hand side, we can't simplify at this point because it depends on the form of r of x and it depends on the form for mu of x. Okay, so we just leave that as an integral. Okay. And since we are doing an indefinite integral, we have to add a plus c here. So we have to add our constant. Okay. And then finally, the last thing we have to do to simplify and solve for y of x is just divide by the integrating factor mu of x. Okay. And so in the end, you know, once you do all this, you'll be able to solve for y of x. Okay. You can take this derivation kind of one step further, and you can get like a formula, I guess, that you can plug in for you know, for y of x, for integrating factor. And if I'm being honest, you know, when I first learned integrating factor, I just kind of plugged into that formula. But I think, you know, when you're doing these types of problems, I think it's more important not to plug into that formula, but instead to kind of follow this process, just so that you know kind of what's going on, because it's, you know, differential equations is, I think, a little bit different than some of your other math courses where you know, it's more than just kind of plugging into a formula. It's more about kind of, you know, following a process and kind of knowing kind of what you're doing throughout that process. Okay. And so integrating factor problems kind of fall into 3 steps. And so step 1, well, I guess step 0 is determine if you can use an integrating factor. Okay. Step 1 is just to compute the integrating factor. Okay, so you're going to use that formula. That is one formula that you have. You have to use that formula to compute the integrating factor. Okay. Step 2 is to form this form and integrate both sides. Okay. And then finally, step 3 is just divide both sides by mu x. All right. Any questions on that before we do an example? Yeah.
So for this one, it doesn't matter if the x component is squared,
Yeah, so X can be whatever it wants here. So X can be squared, it can be exponent, it could be, you can even be a sine or cosine too. So the only one that matters here is just the Y. So the Y is the only one that has to be. Yeah, good question. Okay, so let's do an example. Let's do an example borrowed from electrical engineering, actually, just because it blends pretty well. It also leads into your homework as well. So there's a homework problem that's similar to this. Okay. Not quite like this, but similar. Okay, so let's look at an RL circuit. So an RL circuit is a very simple circuit that consists of a resistance and an inductor. Okay, so that's what the R stands for resistance, L stands for inductor. And let's put a battery in there as well. Okay. Okay. So let's go ahead and draw the circuit first. Okay. So sometimes it's a little bit hard to tell because my art skills are not that great. I also drew that inductor backwards. That's why it kind of looks weird. But the little kind of sharp squiggly lines up top, that's the resistance. The circular squiggly lines at the bottom, that is the inductor. And the one thing on the side there is the battery. Okay. So in this case, we have a DC, we're gonna have a DC battery. So that means our battery is going to provide a constant voltage source. Okay. Okay. So if you have an RL circuit like this, what you can do is you can apply Kirchhoff's laws for circuits. Okay. We're not going to go through the actual Kirchhoff's laws or how we actually obtain this differential equation. We just want to solve the math problem. But I just want to show you that you can this is I think our first physical situation that actually gives us a differential equation. Bless you. Okay. By applying Kirchhoff's laws, we can get a differential equation that describes the time evolution of current in the circuit. Okay. And so the current is given by the symbol I. So you have di dt plus R over L times I is equal to E over L. Okay. So a very simple, first order linear differential equation for the dependent variable I. Okay. Okay, and then just to be a bit clear here, R, L, and E are all constant. Okay. Okay, so that's our differential equation, and what we want to do is we want to solve this differential equation for the time evolution of current within the circuit. All right. So here we have kind of our first order differential equation. It's we took one extra step here, just showing you that it came from a physical situation. But at the end of the day, here we have something that we can solve using integrating factor. Okay. Any questions on just the setup of the problem? Okay, good. All right, so let's go ahead and solve this with integrating factor. Actually, if you try to solve this with separation of variables, you can't because there is a non-homogeneous term there. Okay. All right, so let's go ahead and execute kind of our three-step process for solving a problem like this. So step one, well, step zero, we've already identified that this is an integrating factor type problem. Step one is to compute the integrating factor. Okay. So in this case, pay attention to what your independent variable is. And so I think above our independent variable is x. This time it's t, but it's just kind of a change, just a change in letter, but they function all the same. Okay. So our integrating factor mu of t is going to be e to the integral. Our p is r over L in this case. Okay. So you have e raised to the integral of r over L dt. Both r and L are just constants, and so we just have integration of just dt by itself. And so our integrating factor in this case is fairly straightforward. And so our integrating factor is e raised to the r over L t. Okay. Good. Step two. Step two in our integrating factor methodology here is to multiply this integrating factor by the differential equation and form the perfect differential on the left-hand side. Okay. So on the left-hand side, we have I of t multiplied by mu of t. Okay. So we have d dt on that side. And on the right-hand side, we have e over L multiplied by mu of t. Okay. Okay. Of course, we already know what mu of t is, and so we can actually plug that in. Let me actually do that right now. Okay. So we know mu of t is e to the r over L times t, and on the right-hand side, this is e to the r over L times t. Okay. Okay. So let's go ahead and integrate it. And in this case, we're integrating with respect to t. Okay. And so on the left-hand side, we have I of t multiplied by e to the r over L t. Okay. And on the right-hand side, we have e over L. E over L is just a constant, and so that can just be factored out of the integral. And we have integral of e to the r over LT. Okay. You can, I think probably the most, I guess, straightforward way to do this is to do u substitution. So you can do u is equal to r over LT, and then go through that whole process. Or you can just kind of shorthand it. And just know that, when you take the derivative of e to the r over LT, you get r over L times t. So if you're integrating that, you kind of have to do the opposite. So to integrate, this becomes L over R, e to the r over LT. Okay. So this new factor here comes out in the integration. By the way, I know, for for, for a lot of people, it's been a while since you've done some integration, and we're gonna be doing a lot of integrating in this class. And so I actually did post an extra handout on the Canvas site to kind of refresh your memory on two very common integrating techniques that I use in this class. And so if you go to the Canvas site and you go to the page for week 2, you'll see there are 3 files posted there. So the first file is the first order notes that we're going right now. The last file is the notes we're going to do next, which is on second order ODEs. But the file in the middle is the integration help. Okay. That is file 1A integration. It's like integration helper.pdf or something. So definitely check that out if you feel a little bit rusty on your integration, because we're going to be doing a lot. And for the most part, I'm going to be kind of going a little bit faster in the integration. Okay. And then, of course, because we did our indefinite integral there, we have to add a plus C that we're going to be specifying in a second. Okay. All right, any questions on this so far? Yeah.
How do we determine the P of X again?
The P of X, that is something that's given to you in the problem. So you would go back to the original problem, and then just whatever term is multiplied by your dependent variable, that's going to be your P. Although that does bring up a good point where, if your equation is not in standard form, so let's say that, there was an additional 5 right here, okay? First thing you have to do is you would have to divide this entire equation by 5 to make sure the coefficient in front of the derivative is 1. Okay, so that's one thing to be careful. I think for the most part, I'm going to give you cases which are already in standard form, but just kind of watch out for that. Right. Any other questions on this part problem so far? Okay. Good. Okay. So now that we have the equation in this form, we can go ahead and move on to step 3. And so step 3 is to just divide the entire equation by mu of x to isolate I of t in this case. Okay. And so when we divide by integrating factor, we arrive at our general solution. Okay. So we have I of t is equal to, and by the way, these L's are going to cancel out. Okay. Okay, I of t is equal to, so we're going to divide both sides by e to the r over L times t. That's going to cancel out with this one. Okay. So this first term here is just going to be e over r. Okay. And then we have c times e to the r over L times minus e over r, minus r over L t. And that right there is our general solution. All right. So that's how you apply integrating factors. So for a linear first order differential equation, integrating factors, I think, are the easiest to kind of do. If you feel more comfortable with separation of variables, you can do that. But, with separation of variables, you can only do that for homogeneous equations. Since this equation had a non-zero right-hand side, and so in other words, it had a term that didn't have I or T in it, then, it's much easier to do with integrating. Okay. Now, at this point, we're not quite done yet. So we do have to specify a value for C, right? So C right now is still an arbitrary constant, and we can solve for its value by applying an initial condition. Okay. We can do that in a second. Okay. But before I get to that, I do want to point something out to this solution, because even though this solution is quite simple, there is some very interesting kind of behavior to it. Okay. And it brings up a really important application for differential equations in terms of analysis of engineering systems in general. And so very common kind of application and a big reason why we analyze systems with differential equations is so that we can analyze what's called the transient part of the solution and the steady state part of the solution. Okay, so what do these mean? So, whenever you have a physical system, oftentimes there is certain behaviors that only occur for a short period of time, and there's some behavior that occurs over a long period of time. Okay. So some important short-term effects would be things like, from a structural point of view, let's say that, you take your structure and you apply some kind of impulsive loading to it, right? That's a very fancy way of saying, let's take a table, and let's just punch the table, okay? Versus a long-term effect. So let's say that, you have your table and you are resting, a 100-pound weight on the table, right? And that's going to persist over a long period of time. So you want to find out, how is the table, or how is your structure, or how is your engineering system going to behave in the short term from very kind of quick, fast loading versus, over a long term if you apply things, over a long period of time. Okay. So short-term effects, we often call these transient effects. Okay. The term transient just basically means, it doesn't persist over long times. It's transient. And so it's here for a short period of time and then it kind of goes away. Okay. And then long-term effects, we often call these steady state. Okay. So there's different terminologies for these things. And what's interesting about, the solution to a differential equation is that oftentimes you can tell from the solution, which parts will be transient and which will be steady state. Question, yes.
What passes as short term versus long term? 10 minutes be long term?
Yeah. So the right answer to this question is that it depends on the system, but oftentimes for short term you're talking about in a matter of seconds, and then long term will be over even up to a couple minutes. That's usually pretty long term. So short term means like very immediate effects, and then long term is something that persists for long. Okay. So you can tell what these effects are going to do based on the solution. So actually, let's go back to our solution to the previous example. Okay. And let's see if we can identify which parts of the solution are going to be transient and which ones are going to be steady state. Okay. Remember, the dependent variable in this case, or excuse me, the independent variable is time, right? So little t there stands for time. Okay. And so let's look at, so we have two terms in this solution. So we have an E over R, and then we have a C times an E to the minus R over L times T. Okay. So we'll call this term A, and we'll call this guy term B. Okay. Okay. So what I want to do is let's look at this, let's look at each of these terms here and let's see what happens to them as time gets large. And so as time gets to 100, 200, 300. Okay, so let's look at term A first. So term A is E over R, excuse me. So what do we know? We know that E, in this case, we have a DC circuit, so E is a constant. And R is a constant. Okay. And so E over R here is just going to be a constant. It's going to be, just some number. Okay. And so what happens to this term when time gets large? Okay. Nothing, exactly. So that's exactly what happens. So since this term doesn't depend on time at all, as this term actually doesn't even care that time is getting large. So this is something that persists at large times. Right. And so since this is something that's going to persist at large times, what we can say is that this is going to be a steady state effect, or this is going to be a steady state part of the solution. Okay, now let's look at term B. Okay. So B in this case is C. It's a little awkward because we haven't determined C yet. Went on a tangent a little bit. Okay. We have C times E to the minus R over L T. Okay, so in this case, C, R, and L, all these are constants. Okay. But the important behavior here is essentially we have a decaying exponential, right? So we have E raised to the minus tau. And so what happens to a decaying exponential as t gets large? It goes to 0, right? So as t gets large, then this term here is going to go down to 0. Okay. And so what does it tell us? And so what this tells us is that this term or this part of the solution is only going to persist for a very short period of time. And so what does that tell us? That tells us that this part of the solution is going to be transient. Okay. Okay. So this is a theme that's going to persist, it's going to be steady state over the next, 4 or 5 weeks. And so definitely look out for this. And so, not only is this going to be a thing in our first order equations, it's going to be a thing for our second order equations. We're going to stop there for the Laplace transforms as well. So every time you solve for a solution to a differential equation, especially the ones that have time as an independent variable, so a lot of times those are going to be our physical problems, or our application type problems. Look and see, which parts of the solution are going to be steady state and which parts are going to be transient. Right? And the question to always ask yourself is, what if time gets very large? So as t gets to, 10, 100, 1,000, what's going to happen to certain parts of the solution? And that tells you whether it's going to be steady state or transient. Okay. All right. Any questions on this? Okay. All right. So very quickly, let's finish up this problem. So let's go ahead and apply an initial condition. I don't think I gave you one in the problem statement, but let's assume that we start with a zero current in the circuit. Okay. Generally, that's what you want to see when before you connect a circuit. You don't want there to be any kind of electric charge on the circuit. You don't want to connect something and then get hurt. Okay. So let's apply that initial condition to our problem. So our general solution I of t is E over R plus C e to the minus R over L times T. Okay. Let's go ahead and apply our initial condition. So let's plug in 0 for T. So if I of 0 is equal to E over R plus C e raised to the 0 power. Okay. Then all that's going to be equal to 0. Okay. E to the 0 power, that's just going to be 1. And so this lets us solve for C. And so this tells us that C is equal to minus E over R. And if we plug that into our general solution, we get I of t is equal to E over R minus E over R, E to minus R over L T. Right. Any questions on this example here before we move on? Cool. All right, let's do one more example with integrating factor, just to kind of give you another look. For this example, we're going to go back to y and x. So this is just a math problem. So no circuit, no kind of physical application for this one. Okay. Okay, so for this problem, we have y, or x, excuse me. I wrote x and my mind said y. X times dy dx plus 4y is equal to 8x to the 4th. Okay. Okay, and then we have our initial condition, y of 1 is equal to 2. Okay, good. All right, so first thing, let's check here. So let's check to see if we have a linear equation. So let's check all the powers of y. So y only appears once in this equation. Okay, it's right there. And we can see here that y has a power of, is raised to a power of 1. So we do have a linear equation. Okay. But actually, this is a good example because this brings back the point that someone asked about earlier. What is the p of x in this situation? Okay. You might look at this equation and be like, all right, p of x is equal to 4, so we should just integrate that for our integrating factor. But we actually have an x out in front here. Okay. Before you apply integrating factor, you have to make sure that the equation is in what's called standard form. Okay. Standard form, all that means is that the highest order derivative has a coefficient of 1 in front. Okay. So before computing integrating factor, Okay. So standard form for any differential equation, not just first order equations. So we'll see this in second order equations soon too. Is that if the coefficient of the highest order derivative is 1, then that is standard. Okay. So for this problem, we're not in standard form because the coefficient for the highest order derivative, dy dx, is x. So before we do anything, before we compute any integrating factors or move forward, we need to divide this entire equation by x to get it into standard form. Okay. And so dividing this entire equation by x, okay. So dividing this entire equation by x, we get dy dx plus 4 over x times y is equal to 8x cubed. Okay. So the second term of our expression here becomes 4 over x, and our last term loses 1 power of x, and so instead of being 8x to the 4th, we have 8x cubed. Okay. All right, now we can compute integrating factor. So mu of x in this case will be e raised to the integral 4 over x dx. We have an integral of 1 over x in this case, or 4 over x technically. So integral of something over x is just natural logarithm of x. So e raised to the 4 times ln of x. Remember, we don't need to add plus c here just because the integrating factor is kind of its own thing. Okay. All right, so let's simplify this, and so let's apply the really convenient rule for logarithms, and that if you have some constant multiplied from the out in front of the logarithm, that then becomes the exponent of the term inside. So what I'm gonna do is I'm gonna take this 4 and pop it inside the logarithm, and so that'll become x to the 4th. Okay, so equal e times ln x to the 4th power. Okay. So now that we have the ln kind of exposed in front, that can cancel out with the e. And so all we're left with is an integrating factor, which is x to the 4th power. It's a little bit of an unusual integrating factor here. It's usually integrating factor has some exponential, but in this case, the logarithm and the exponential kind of cancel out. So we have just a polynomial. All right, any questions on how we got that integrating factor there? Okay, cool. All right, so let's go ahead and move on to step 2. Okay. Now that we have our integrating factor, let's multiply it by our entire equation and form the perfect differential on the left-hand side. All right, so we have d dx of y of x multiplied by mu. Mu in this case is x to the 4th power. Okay, that's equal to 8x cubed multiplied by x to the 4th. All right, so let's go ahead and integrate this. And so the integration on the left-hand side is going to cancel out. So we have y of x times x to the fourth. Okay. 8x cubed times x to the fourth, that's x to the seventh. We integrate x to the seventh times 8. That's just going to give us x to the 8th power. Okay. And then we're going to add c to the whole thing. Okay. All right, and so our last step here is that we're just going to divide this entire equation by the integrating factor. This is a pretty straightforward step. We're just going to divide by x to the fourth. We have y of x is equal to x to the 8th divided by x to the fourth is going to be x to the fourth plus c divided by x to the fourth power. Okay. Okay, so there we have our general solution. All right, before we apply our initial conditions here, let's look at this. Let's look at this solution and let's see if we can identify which part is transient and which part is the steady state. Okay. So once again, we have two terms in our solution. We have an x to the fourth, and then we have some constant divided by x to the fourth. So let's see what happens when x becomes a large number. Okay? And so when x becomes a large number, what happens to x to the fourth? Some large number raised to the fourth power is going to be something very, very large. So x to the fourth here, technically this is a term that kind of, well, we say kind of blows up, and so it goes towards infinity. But technically it's non-zero at large times. So we say this part of the solution is steady state. Okay. And so it's non-zero at large values of x. Okay. And then we have c divided by x to the fourth. And so here x is in the denominator. And so when x goes to some very large number, you have some large number raised to the fourth power, which is going to be some very large number. But then if you divide by it, you have some constant divided by a very, very large number. And so that's going to trend towards 0. Okay. So this part of the solution here will be transient. Okay. It's transient because it disappears at large x. Okay. All right. Let's go ahead and apply our initial conditions now. So our initial condition was y of 1 is equal to 2. Okay. So let's go ahead and plug that in. So we have 1 raised to the fourth power plus c divided by 1 raised to the fourth power. Okay. And so if we simplify this, you get 2 is equal to 1 plus c. And so very quickly or very easily, we can see that c in this case is going to be equal to 1. All right, and so then our final solution, y of x is equal to x to the fourth plus 1 divided by x to the fourth. Any questions on that example there? Yeah.
Would you explain the steady state and transient?
Sure. So when we talk about steady state and transient, we're looking to see, which parts of the solution, when we plug in a large value for the independent variable, which one of those are going to persist and which one of those are going to go down to zero, right? And so we have two very different types of functions here. So we have x to the fourth power, right? And so, what's going to happen to x to the fourth power at large values of x? So at large values of x, to the fourth power is going to be some very, very large number, right? And in fact, if you graph it, right, the graph of x to the fourth power looks something like this, right? And so as you get kind of further and further away from the origin, this function is going to get very, very large. On the other hand, we have 1 over, well, I know it's c, but we essentially have 1 over x to the fourth power, right? And so what happens to this type of function when x becomes large? And so since x is in the denominator this time, you have 1 over a very large number, which is going to be basically equal to 0. Maybe not quite equal to 0. It's going to be some very, very small decimal, but it's going to get decayed down towards that. And in fact, if you graph it, right, the graph of 1 over x to the fourth looks something like this. And so it kind of, asymptotes down to 0. It doesn't quite get down there. It's going to be 0.00004 or something like that. But, it gets very, very close. And so you want to look and see what the behavior of the different terms are at large values of either x or t. Then make a little more sense. Okay. Any other questions on this before we move on to second order equations? Okay. All right, so we have about 15 minutes left. So I'm going to go ahead and introduce the concept of second order equations now, but of course, we'll do most of the examples and stuff next time. Okay, so let's look at second order linear ODEs. Okay. Okay. So a couple of things. So second order now means that we're considering equations with a second order derivative. Okay. And that's actually going to change things quite a bit. And so it's going to change, basically change our entire process. So there's no more separation of variables. There's no more integrating factors. So we're going to use an whole new method. Okay. But the other part of this that oftentimes gets lost in the wash is that, we're only considering linear ODEs at this point. Okay. And remember what linear means. Linear means that y and all of its derivatives only appear with an exponent of 1. Okay. The coefficients of y can do something different. But all the y terms itself are only going to be 1. Okay. In fact, let me go ahead and show you the standard form. Okay. Standard form is y double prime. Actually, no, I promise you I wouldn't do this. So standard form d squared y dx squared plus p of x times dy dx plus q of x y is equal to r of x. Okay. All right, so first thing, let's just check to see if this form is linear. So we have three y terms now. So we have y by itself, we have its first derivative dy dx, and we have its second derivative d squared y dx. Okay. So don't be confused. It's a little bit confusing because the second order derivative, we have exponents here. Those exponents are only in the derivative. And so if you look at the overall exponent for the term, okay, right? The overall exponent for this term is 1. Okay. So y and all its derivatives in this case all have an exponent of 1. So we are in a linear case. Okay. That's good. Okay. It's also standard form because now that our highest order derivative is second is 2 now. Right? If you look at the coefficient in front of the highest order derivative, it's 1. Okay, it's implied there because we don't write 1 times something because that just equals to something. But that it's implied that the coefficient in front of that highest order term there is okay. All right. Another piece of terminology has to do with the right-hand side here. Okay. So R of x, this was something that we saw with integrating factor. And so this R of x here, this is what we call the inhomogeneous term or non-homogeneous term. Okay. And so we're going to solve two types of equations in second order equations. When R of x is equal to 0, we call this a homogeneous equation. And when R of x is not equal to 0, this is non-homogeneous. We're gonna focus mostly on homogeneous. So I know for sure all of Thursday we're gonna talk about homogeneous equations. We probably won't get to non-homogeneous equations until sometime next week. Okay. That's actually a whole another thing that we have to solve too. So just kind of hold on to that for a second. Okay. So what's different about second order equations than first order? One kind of unique thing about second order equations is that we're actually going to get multiple solutions to the problem. In fact, since our equation is second order, that means we have two solutions that can satisfy these equations. So that means you can solve the problem, get one solution, plug that back in, and it'll satisfy the equation. And you can solve the equation with another one, plug it back in, and that's also going to satisfy the equation. Okay. So all second order equations, we're going to have two solutions. We'll call it y1 and y2. Okay. And so we'll say both of these are going to satisfy the original ODE. Okay. Remember we talked about last Thursday that the way to check it to see if a solution satisfies an ODE is just to simply plug it in, right? And so y1, y2, you plug it in, it's going to satisfy the original ODE. Okay. But it's a little bit cumbersome to kind of remember two equations at once. So oftentimes, we often report these as a single solution. And so we often combine these together into one solution that we often report. And the way that we combine them together is we just simply add them together. Okay. So this idea that you can take two independent solutions and add them together and still have a valid solution, this is known as the principle of superposition. Okay. And the idea is that the combination of these two, or the superposition of these two, will still be a valid solution. Okay, and so the superposition of these two solutions looks like the following. Okay, so oftentimes, when we solve a second order equation, we combine these two solutions into one. And so what we say is that y of x is equal to c1 times y1 plus c2 times y2. Okay, where c1 and c2 are arbitrary constants. Okay. And oftentimes we solve for the values for C1 and C3 through the use of initial conditions. Another name for this technique here, to take two functions, multiply them by an arbitrary constant and add them together, is to take what's called a linear combination of these two solutions. Okay. So this is something that's unique to second order equations. And in particular, it's unique to second order linear equations. And so everything that we just talked about for the past 10 minutes, if your equation was nonlinear, then none of this really applies. Nonlinearity is really difficult to deal with. We can only really deal with it in the first order equations. And even that's in very specific situations where you can do separation of variables. And so, you want to try, when you kind of get further along in math and you kind of get further along in analysis, you kind of just pray to the math gods that you're not working with a nonlinear situation, because nonlinearity just it just messes everything up. You literally need a whole new textbook to solve it. And so, luckily for us, at least for this class, we're only going to deal with linear solutions for the vast majority of cases. But just know that nonlinearity is out there. It's scary. Okay. All right, any questions on this? Okay, so there's a proof which kind of proves to show that you can take a superposition of two solutions and that combination is still a valid solution. In the interest of time, I'm going to skip that proof. Okay. Last thing I want to talk about today is the concept of linear independence. Okay. So one requirement that we do have for when you have separate solutions to a second order ODE, so we have y1, y2, is that they must be linearly independent. Okay? So what does that mean? So linearly independent must mean that, or basically what that means is that, you know, one solution cannot be just linearly proportional to another solution. So the easiest way that I like to think about linear independence is that your two solutions, you know, must have different functional forms that you simply just can't add them together. Okay. All right. Okay. And so I think the easiest way to kind of illustrate this is with just a few examples. Okay. Okay, so let's say that we have our first solution, y1 is equal to x, okay? And our second solution, y2 is equal to 4x squared, okay? Are these two functions here linearly independent? Okay, so our first solution here, that's a linear function in x. Our second solution, y2 is x squared. That's quadratic function. So both of these have unique functional forms. So yes, these ones are linearly independent. You can't simply just add x to 4x squared and get one term simplified together. Okay. All right. What about y1 is equal to 7x versus y2 is equal to 4x? Okay. In this situation, both terms are linear functions in x, and so you can just add them together. And so if you add y1 plus y2, this simplifies into one term 11x. And so in this case, no, they're not independent. They have the same functional form. They are both linear functions in x. Okay. One last one before we wrap up, just because this is going to be a common case. Let's say y1 is equal to e to the 4x versus y2 is equal to e to the 7x. Okay. So here we have exponential functions. Okay. Are these two functions linearly independent? Yes, because you know the exponents in both cases are different. So you add e to the 4x, you add to e to the 7x. It doesn't become e to the 11x. That's not how exponents work. And so since these two are unique functions, they are independent. All right. Any final questions on this before we wrap it up for today? Okay, all right, so when we come back on Thursday, we'll continue on with our discussion of second order equations. We'll talk about how to solve homogeneous equations and then go from there. All right, so thank you guys for coming today. Hope you guys have a good rest of your evening. And I will see you on Thursday.
Yeah.
I get this, and I said multiply this on the entire equation.
Yep.
This equation,
Yes.
where did the y on top of dy?
Yeah, so in this case, that was kind of the derivation we talked about last week. Right, but and I entire back in five becomes the perfect differential of y of x times the integrating factor. And take it correctly. Yeah, so that's kind of the whole purpose of the integrating factor, the form this size.
Oh, right.
Yeah.
Oh,
Oh, yeah. So I would catch up. So the recording is up from last week.
you report all the.
Yeah, so you go to the Canvas site, exactly.
Oh.
Go to the Canvas site, go to week 1, and then there will be a YouTube link there for week 1 lecture.
Saw that and I was like, no way he actually does that. I was like, but it's nice.
Yeah.
I'm glad you do that.
Oh, yeah, all the lectures are recorded. So usually I put them up by the next day. So by tomorrow, yes. I record on Zoom, I download the file and I just upload it. For Zoom, I think they won't keep it up for like 2 weeks or something.
Interesting.
Yeah, like YouTube.
So this is not live.
This is live.
Oh, this is live.
Yeah.
Like say, for example, I wasn't here, I could just tune in.
Yeah.
Really?
In fact, yeah, most people actually do that. So if you go to the Canvas site, there's Zoom links there too, so you can attend it.
I have a question.
Yep.
So for separable, you can have multiple and exponent for y?
Yes. Yeah.
Okay.
This is the one case where we can do nonlinear stuff. So yeah, so in this case, you can do y to.
Okay, so how would, because I don't think I did this in my last math class, I'm pretty sure you only did y to the first.
Yeah.
So that's why when I looked at this, I was trying to figure out what to do.
Yeah.
But how do you differentiate this from Bernoulli's then for
Oh.
linear?
Um,
Because I know you can have y to the exponent of something.
Yeah.
So then it kind of looks similar.
yeah,
I did extra.
yeah, that's interesting.
Because I was looking at this, and I'm like,
Yeah.
okay, well, it can't be linear, and then I'm like, oh, Bernoulli, and then I was trying to divide it and all that.
Yeah,
I just didn't realize.
Yeah, I think for this case, we're gonna focus just on separation.
Okay.
Bernoulli's is valid. And so I think you could probably use Bernoulli's for this one too. I have to kind of refresh my memory.
Yeah.
It's been a while for me too. But for this one, yeah. so
Yeah, just separable.
Yeah, just so if you see y to the second power third, just say it's a separable.
Okay, thank you.
I'll see.
I had a quick question.
Sure.
This one is the actual answer that we have to get.
Yeah, so I did hear people were saying that there might be mistakes, so I might double check that one. So if you're not getting that one, just send me an email. I'll double check my solution. Just
Okay.
Yeah.
Thank you.
Yeah.